So the last week was mostly review of the material you guys already know. So this week what we are going to do is we are going to start with material relevant to this course.
You have the person that's even popped on in the
So let's start with, think about, recall relative motion. Okay. So what we did was we discussed something like this. You have an inertial reference frame. I, J, and Q. And then you have, this is point 1. We have mass m1 and mass m2. The position of this mass for the center, no cell phones. Yes. Position of this mass, or the position vector of this mass m1 would be represented by r1, and let's say this is r2. Okay, these are the absolute positions because this is the inertial frame. Okay, now the relative position, let's call this R. Okay. Now what is R? How would you represent R in terms of vectors?
R naught plus R delta.
In terms of R2, R1 and R2? R2 minus R1. Does this make sense? You see, R1 plus this R is equal to R2, right? So this R is equal to R2 minus R1, and this is the relative position of M1, here generally what we'll do is we'll say R is relative position of M2 with respect to M1. Okay. Now, what is the force of attraction between
Wait, can you explain that? Like, what do you mean?
relative position of M2? R1 is the absolute position of M1 because it is in this reference frame IJK. R2 is the absolute position of M2. But in reality, it's very difficult to find this inertial reference frame. There is no inertial reference frame. So what we do is, we can express the position of one body with respect to the other body. And that's what we are interested in. So let's say, think about this M2 as moon, and this could be Earth or Sun, for that matter, anything, right? So now we can say this R as the position of moon with respect to Earth. So relative position of M2 with respect to M1. Okay. And this R, you have to keep in mind, R is R of t. Got it? Because this is constantly changing. It's a function of time. Now, if you apply, just think about this for a while. If I say F12 is equal to G M1 M2 divided by R square in the direction of. So this F12 is defined as the force of attraction. What is the force of attraction? What direction is the force of attraction M2 with respect to M? So you can see, can you see this is F12?
And you said what's what?
So there are two forces, right? M1 will be attracted to M2. Similarly, M2 will be attracted to M1. Got it? Because that's what Newton's law says. The force of attraction of M2 towards M1 is in this direction. Right? Similarly, the force of attraction, this would be F21.
There's no positive and negative position though within those forces? Like if one is going that way, would it be a positive force of action? It doesn't
So you
matter.
can say F12 is minus F21.
Okay.
Okay. So the direction itself it should tell you the positive and negative. Right? Now, here what you can do is you can say
It's not a T.
That's all.
now this should make sense to you. Does this make sense?
Yeah, because the original is negative, right?
What?
I was saying it does if they're going opposite ways, then it should be negative.
Right. So this R, which direction is this R vector?
Say which direction?
So that R cap is what direction? It's this direction, right? So we have defined R as from here to here. Right? So R cap is in that direction. Till
Okay.
So G is negative.
G itself is not negative. G is a constant. But this, if you have to look at this F12 and this R.
Oh, okay.
Okay. So if they are in the same direction, so here F21 and R are in the same direction. Okay. So this defines what I've done here is simply applied Newton's law of universal gravitation. Yes.
Why is the R vector? Does it have to be from the bigger mass to the small mass in that direction, or could it be the opposite direction?
So here both of them have been captured. This is the force of attraction on body of M2 with respect to M1, which is in that direction. This is force of attraction of M1 with respect to M2, which is in this direction. Now, if we define this R is in this direction, right? So this R cap would be what? Simply R divided by
Magnitude.
magnitude.
So that F12 equation is negative.
F12 is negative. Negative just means the direction. It will just tell you what direction it is. That's it. It doesn't mean anything other than the direction. Okay? It defines. Now, what you're trying to do is we're trying to understand relative motion of body M2 with respect to M1. That's what our goal is. Now, similarly, if you can also say F12 is equal to d over dt you can apply so here we are going to use the see here we are going to use the shortened form of this is Newton's second law, right? Keep in mind, m dot is not changing. The mass is not changing. So we can assume this case of the law. This is Newton's universal law of gravitation. Law of gravitation. Now you can see, you can actually combine these two. Okay. To get, I won't get into the derivation, and I won't expect you to know the derivation.
Wow.
This is called two-body problem, and this is very, very important. This is where everything begins for this course.
So
Huh?
in the Newton second law equations, that M is it the combined mass of 1 and 2?
Right. So this is M1, which is okay. Okay. So here, this defines. This is a two-body problem statement, and you have to get a little bit of context into what this law means, or what is the significance of this law. This law is derived under three assumptions. M1 is much greater than M2. Or what we do is we'll use capital M for the mass of the larger body and small m for the mass of the smaller body. Okay. So what does this mean? Now think about what does this mean. Okay. If you have two masses, right, where would the center of gravity of this mass be? Of this system, two mass system be? It will be closer to the large mass, right? With this condition, this mass moves, the center of gravity moves so close that it will practically be the center of gravity of the mass 1. Okay. So the center of mass 1 is the center of mass of the two systems. Got it?
That's not negative, is it?
Which one?
The bottom, the last one, the last row.
The
The last row.
He's just that's the first bullet for the three.
That's the first one. So this M1 is the mass of large body, and this M2 is the mass of yes.
Question. So, in regards to like the Pluto system,
Hmm?
like you know, how Pluto is how Pluto is moon, they kind of like have a central moon on the front.
Hmm.
Is that because they're relatively the same size, or?
Yeah. Not the same size.
Right. So if you look at the recent study of Jupiter, right? Theoretically, what you should know is Sun and let's say Earth. Earth is not revolving around the Sun. Sun's gravity. There is any two bodies are revolving around their center of mass. Sun is also wobbling a little bit in its position, right? So whatever the center of gravity. So if you have this, right? If this is your Sun, you guys can see it. So if you have, let's say you have this is your Sun and this is Earth. So Earth is not doing like this. Okay? Sun and Earth are doing like this. They're the center of mass of these two systems around which these two are rotating. It so happens that this mass is so big, this is doing only like this. It's hardly noticing. And this Earth is doing this. Okay? This becomes much more noticeable. For example, if you look at Sun and Jupiter, you'll see much more wobbling of the Sun. You understand why that is the case? Why is that the case? So this mass becomes, see, as when this is really small, the center of mass of these two systems is almost close to the center of mass of M1. If this becomes significantly larger, now this becomes, let's say, Jupiter, right? The center of mass moves away. The center of mass of the system moves away from the center of mass of the larger body. So that time this has to rotate around that center of mass. These two, the two bodies are always rotating around each other's center of mass, or the center of mass of that system. Okay? So this is one of the assumptions. This assumption makes sense?
So how large is Jupiter in comparison to the Sun?
Huh?
How large is Jupiter in comparison to the Sun?
It's probably a few hundred times the size of Sun. Oh, sorry, the Sun is a few hundred times. I don't know the exact thing. I can get you the thing. But it's significantly larger compared to some of the other planets. So it has that. So if you launch a satellite will be much smaller, right? So it's if you look at the satellite and the Earth, their center of mass, the two center of mass of these two bodies, would be at the center of mass of practically at the Earth. Yes.
Is the orbit getting smaller
No.
So you know,
We'll get to that point. So, but they are continuously doing this, okay? But if this is really, really big, so this is hardly doing this, and this is, if it's center of mass, if it's rotating, right? That rotating is because of the center of mass. So this is the first assumption, and the second assumption is, so gravity is the only force acting between the two bodies. If you're studying the two body, right? Gravity is the only force acting between the two bodies. Is this true for all satellites? Is this true for space station? What other forces are acting if you're looking at the space station? So space station is also an orbiting body. You think of that, right? You know that. What does this mean to you guys? The gravity is the only force acting between these two bodies. Are there any other forces acting? External forces.
Is inertia external? Or internal?
Inertia is not external.
Say other bodies passing by would be external forces.
So that is the scope of our is only two bodies. So let's look at it at that point. You are right, but that's a little more complicated.
You talking about the space station?
Space station and Earth, let's say that. So what other forces are acting? Why is space station doing that? Because it's under the gravitational pull of Earth and it has been launched with a particular velocity. So those two, it keeps doing that. But what other forces are acting? Space station cannot stay there. You know that, right? By itself. Quite often, the space station has to.
Just thrusters.
It has to use thrusters to go to the. Why does it have to use thrusters? What's happening?
Hold it there.
That's the increasing mass. Part script skip that's cool.
No, but why is it using the thrusters? Is its altitude changing?
Yes.
Its altitude is changing, it's dropping. Okay? If this was the only force, if gravity was the only force acting on the space station, its altitude would not drop. So why is its altitude dropping?
just
Because of the force
Gravity is pulling it down.
So force of gravity is pulling, right? That acceleration is there to keep it away. So that force is not pulling it down. What is pulling it down is there is still some atmosphere there. Okay? So that atmospheric resistance, that is the external force. There is no complete vacuum anywhere. You understand that, right? Complete vacuum means absolutely nothing. So even as you go into space, there is something somewhere, a little bit of matter. In low Earth orbit, especially where space station is, there is still quite significant amount of atmosphere, and that atmosphere is the external force. So that external force is pushing it down. When it slows down, you'll see, according to these laws, when it slows down, it will spiral away. So that is the reason it has to keep pushing it away.
so for the Earth,
Right.
what do we have why don't we spiral down?
So unless we are under the resistance of something, Earth's atmosphere is actually moving with Earth, right? If there is atmospheric resistance, if there is for example, there is solar radiation as the external force. So over millions of years, it will spiral and slow. Okay? But for our lifetime, or several of our lifetimes, it's not changing significantly. The orbit is not changing. But the orbit is changing very significantly for something which is in low Earth orbit. Got it? there could be solar radiation, there could be atmospheric resistance. You understand? And the third assumption is the central body is spherically homogeneous. Okay? So you understand what this spherically homogeneous means? The M, capital M is spherically homogeneous. What does that mean?
There's so much perfect, perfect sphere.
What does perfect sphere mean?
Symmetrical.
The same radius at every point on the surface.
Right, but spherically homogeneous means the geometric center and the center of mass are the same. The mass is equally distributed everywhere. You understand?
And its own point or each point?
Can you relate geometric mass or geometric center and center of gravity?
It'd be, if it was a perfect sphere, it'd be the center of the center.
It will both be at the same point, right? If it is not a perfect sphere,
It would loop around.
right? If the mass distribution is not equal, the geometric center will actually be at the center, but the gravity center of gravity will be wherever that extra mass is. You get it? What would your geometric center be as human beings?
It would depend on the gender.
It would depend on the gender, but what you would do is,
I'm just saying.
you look at principal axis and you'll about that. If you draw x, y, z, your mass is equally distributed. That's what it means, right? But your center of gravity could be very different depending on which part of your body is heavy. Got it? So if you look at so here, well, I guess you guys understand center of gravity and mass center. Sorry, geometric center. Is this clear? What this central body is spherically homogeneous? Anybody doubt with regard to this? You're good? So here I want to stress this enough. This is the basis for most of the developments in the course. Okay, you have to be very, very clear with this and you have to remember this. What is this R? This R? What do you say? How do you say this? This is the relative position of mass M2 with respect to M1, or relative mass of the orbiting body with respect to the central body. Got it? What is this mu? Mu is the gravitational constant. It's generally Gm. Okay, Gm is so this G varies. G and M are. Is this mu going to be the same for, let's say, if you take Earth and Moon, Earth and space station? No? It will be the same. Because this mu relates to, this is the central body, the gravitation of the central body. This is mass of the central body. Now think about Earth and Moon, Sun and Earth. Is this mu going to be same or different? Because this gravitational parameter is, this G is different for Sun.
You go to the sun.
Huh? Yes. Right. So it will be Sun, this will be Sun. For Earth and Moon, this will be Earth. This will be Earth. Got it? So this mu relates to the central body. What central body you are talking about? So Earth, if you talk about Sun and any other planet, this mu will be the same. If Sun is the central body, got it? Sun, Earth, Sun, Mars, Sun, Jupiter, this mu will be the same. If you're talking about Earth, Moon, Earth, space station, Earth, some satellite, this mu will be the same because the central body is Earth. Got it?
So the
But
central
one
body
word,
is
one
the,
word, one word to change? One what?
When the central body changes.
Oh, okay.
so the central body is the larger mass.
Correct.
Okay.
Right. So if you're, what we are trying to study is try to understand what we are trying to study. In a historical perspective, we've always been interested to know where the planets are, where the stars are, where the different comets, what is their path, right? We were always interested to know that. So what did we figure out? We did a lot of observations and we related. We don't know. Universe is so big, we cannot have an absolute position, an absolute path, right? We have to define that path with respect to something. So that's what we did. We defined with respect to where we were, okay? And that is how we started studying. And this is this is as a result of Newton's thing. Now let's look at Kepler's laws. See, until Kepler came along in the 1600s, late 1600s. Yes.
So, I noticed that two of these R's are vectors and then on the bottom isn't. That's radius, right? R cubed.
This is just the see this, yes, this is just the magnitude of the distance, q. Okay. So look at when we look at Kepler's laws and then we stop it. Okay. So Kepler's first law states that all planets orbit around the sun in an ellipse. Second law.
Is that a trace?
Yes. And the third law is anti-wave.
Okay, just one.
With times.
Is that equal times orbiting the sun?
Right. Equal areas and equal times. Square of orbital time period is equal to the cube of the So let's look at this a little bit. I'll take a couple of minutes, okay? So until Kepler came along in the 1600s, late 1600s, whatever was put out there, right? We believed Earth was at the center of the universe. We believed Sun was at the center of the universe. We believed Earth was flat, right? There were so many theories which came along. But none of those theories had any experimental validation or mathematical proof. You understand? Only when Kepler came along, Kepler, along with his accomplice, so you should always remember this accomplice as well, because of him, Kepler was able to propose these laws. So Tycho Brahe did a lot of observations over actually several years. Brahe, Brahae, BR, yeah. So this is Kepler, Johannes Kepler, and that is Tycho Brahe. Tycho Brahe did a bunch of observations over several years, and what Kepler did was he looked at those observations and did calculations. Okay. So the first law says all planets orbit around the sun in an ellipse. Okay. By this time he had accepted that for our universe, sun is at the center, and the observations proved that. Okay. Does this make sense? If you look at what this means is, again, compare this and this. If they are orbiting in an ellipse, they keep on orbiting in that ellipse for millions of years. Or only it will change slightly over millions of years. But they'll keep on orbiting in an ellipse. Okay? And this is actually not complete. How do you draw an ellipse? And this is where I need you to have those compasses or your geometry box. Have you got your geometry box?
I have one.
Okay. So you have, how do you draw an ellipse? In an ellipse with the sun and one of the foci. Okay. Do you guys remember how you drew an ellipse? In high school, did you try to draw an ellipse? How do you draw it? Yes. So you take 2 points, you take a string. Right, go ahead, Nathan.
Oh, you get 2 points and you take a string, tie it in a knot, and then you just follow the string.
You pull it, right? You pull it and you follow the point.
Yeah.
That is how you draw an ellipse. So those 2 points are the foci. Each point is a focus, or 2 of them, they are called foci. The sun is at one of the focuses. You got it? Sun is not at the center of that ellipse. You understand? Everybody's clear with that? Okay? And this is slightly complicated. We'll come back to this a little later. The third law states the square of the orbital period, time period, is equal to the cube of the mean distance. What does this mean? Or what is orbital time period? Everybody understands orbital time period?
It'd be like a year.
It will be a year for Earth, right? It will be, so if you're looking at the sun, right, at one of the foci, and if you're looking at the time taken by any of these planets to complete one revolution, that is the orbital time period. The square of that time period is proportional to the cube of the mean distance. Why do we say mean distance? Anybody? It's changing, right? So when it is, if you're looking at this, if sun is here, if the sun is at one of the foci, that Earth could come closer at some point and then go far away at some point. So we say the mean distance. So the time period, as the planets go farther away from the sun, what happens to the time period? It increases, right? So that is the reason. Which is the first planet? Which is the planet closest to sun? Mercury. So accordingly, Mercury's time period should be the shortest. Got it? Why is so now do you understand why Mars is, where is Mars with respect to Earth and Sun? It's further away, right? So Mars has a bigger year than compared to Mars. Got it? So it's Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto. Right, just give me, Joanne, give me your attendance. You got it?